Hello. Today I would like to discuss the match asymptotic methods to solve a Laplace equation. So this is a general method to obtain solution of equation where there are two different scales. So the specific goal, suppose you have different scales in your problem and you would like to approximate the solutions both for the small and large scale. So here is an example where you can have a small hole that define one scale, and you have also the solution outside this small hole. So let me give you an example. So suppose here you have a small hole and you have another one which is well separated, so let's call it small hole 1, and this is small hole 2. And here suppose you have an equation to solve. For example, it could be a partial differential equations like a Laplacian of something p plus the gradient p multiplied by a vector field equals f. F is a function, and so now the question is that you can have specific boundary conditions such as u equals 0 on one hole, or u plus du dn with some coefficient alpha 1, alpha 2 equals 0 on the second one. And for example, here you have a third boundary condition like Robin boundary condition du dn equals 0. Yeah, I call u equals p here. And so you need to find the solution. And so the form of the solution is that there is a specific behavior near the boundary, near this 1 and 2. There's a different behavior at a certain distance away. So for example, far away here from, you have a different type of behavior. And so the question is, how do you find the solutions? Why this is important? Because of the renewal of interest in deriving equations and solutions for the diffusion, for example, but other processes in biology. So let me explain slowly the approach with an example. I think it's very important to start with an example, and the rest follows from this. So suppose you are interested in this equation. D is a diffusion coefficient, and you are interested in solving d Laplacian p equals delta Dirac with p equals 0 on two holes. So this is what just we saw in the previous slide. You have two holes, one, let's call it d omega 1. This is another one called d omega 2. Outside these two holes, you assume that on the boundary you have a reflecting boundary condition, that is no flux, no particle can escape. And here you have a delta Dirac at the position x0, and you would like to find the solution p0. And I'll explain in a different class related to morphogenetic gradient what is the meaning of this equation. It's like looking at particles that are emitted at a point x0 that can be absorbed at two sources, two holes, and reflected anywhere else on this. So how do you find this solution? Well, you can remember your class about electrostatic. Let's suppose you know, and I'll show you now how to do this. Suppose you know the solution of this equation, Laplacian G0 equals minus delta Dirac, with dg0 dn equals 0 everywhere. That is, we assume that we look for the solution that has just a single behavior on the entire half plane here. So what is the solution? Well, the solution is very well known, the solution that goes to 0 at infinity. So this goes to 0 when x goes to infinity in all direction. You obtain this by the image charge source problem. So that is, you take these positions, you make a reflection with the same distance here and there. So this is delta at minus x0. You find the solution for the entire space, and you sum, and this is what you get. Okay, so now how you proceed, you take this solution, so you know this solution, and you subtract it to P0. So what do you get? Well, because the 2 satisfies this delta Dirac, the delta Dirac goes away, and you are finally left with the Laplace equation for x in half of the space, that is in here. On each of the hole, because by definition P0 is 0, you are left with minus J0, which is, we call it alpha I, which is what we're using here. And outside the 2 small hole 1 and 2, so here I have assumed that you can have severals up to n, 1 small holes, then you have here, you still get your reflecting boundary condition because both of these solutions satisfy this Robin boundary condition. Okay, so let's move on to the next slide. So for this, I need to tell you what is known for more than 100 years. This is a solution of the classical electrified disk problem. So suppose you have again the Laplace equation on half of the space. So this is one line, this is the boundary. So you have everything, the Robin boundary condition, so you have no flux, dw, dn, everywhere on this part of the boundary except on the small hole. I will take a different color, except on this, on one small hole where you assume that you have w equals 1. And you ask what is the solution. That and you're interested in the solution that goes to 0 when the distance from the window goes to infinity. So there is one interesting scale, which is the size of the window, which we can call here epsilon. And so the solution is well known, and you can obtain it from, for example, the book of Crank about diffusion, I think the last edition, 1976. This is the book of Crank. Or you can just do the calculation, integrate from 0 to infinity of sine mu divided by mu, this exponential minus mu eta epsilon I, which is the size of the whole of size of the whole j, multiplied by this Bessel function. And what is sigma? Sigma is the coordinate inside this plan. So this is called S1, S2. And you have eta. Eta is the coordinate perpendicular here. And so what is the solution is 2 divided by pi arcsine of the radius epsilon j for, this is the whole j, divided by L, where L is this distance. It's the sum of 2 distances expressed with this coordinate sigma. Eta is the coordinate perpendicular, and epsilon I is the radius. And so what is interesting is that when the radius rho, so rho here is the sum of the 3 coordinates, goes to infinity, then you have this behavior, that is w, the solution, wj behave like 1 because it is exactly 1 on the surface, and then it decays algebraically with 1 over rho, and then there is a cubic term, and so this is well known in the expansion of a dipole. So if we continue now, we know the solution for one hole, and we are interested in what is the solution when you have many holes. Well, because the solution of the Laplace equation, we have a linear equation, the solution is going to be the sum of the solution of each Weber solution calculated, computed for each hole. Let's call it I. And here we have a coefficient, so I have added here alpha I, which is minus the Green's function calculated at the center xi, so let's call it xi, which is the center of the hole, and x0 is the point where we had the source, if you remember 2 slides ago. So how do you find the solution? Now we're looking, so we would like to find what are the coefficients IA, and for this we are going to use the absorbing boundary condition on each hole, for which by definition Wi of xi equals 1. So then what we have here is that since W is the solution, it is exactly alpha j. You remember alpha j was minus this. I know that Wi are exactly 1, so I can replace this in here. And I can write a system of equation for each position x1, x2, and so on, xn. Right? This is exactly what is written here. So then you end up having a matrix, because you have for the first one alpha 1 equals, so you isolate the first one, you get A1 alpha 1 W1 of x1 plus A2 alpha 2 W of W1 of x2 plus, and so on. Okay, and so then I will write this, and you do the same for the second coefficient alpha 2, which is again A1 alpha 1, but now you have W1 at x2 plus, and so on. And so you can see here emerging this matrix. So because W1 of x1 is 1, so you are left here with a alpha 1. So you can have this, you can write this matrix M. And what is on the right side, you have alpha. You have all this alpha 1, alpha n that will appear, and what you're looking for is the coefficient A. So you can split the matrix M into diagonal term, which is given here. Just you take the term on the diagonal, which is just the alpha 1, alpha n, and then you take the off diagonal term, and finally what you obtain is this matrix. Well, the job is more or less done. You need to invert this matrix. So you can do it formally, just invert, and you can expand if you want using this 1 plus a minus 1 formula, which is the sum of ak, right? Which is what is written here, and so this is what you can use. And finally, this will give you all your coefficients you are interested in. Let me remind you that the flux at each of the hole is given by this formula, Aj epsilon divided by square root of epsilon square, which is the radius of the hole, minus r square, or r is, so if you have this is a hole, and so if this is the center of the hole, let's call it 0, r is the distance. If you're in the plane, this is easy. This is the distance between 0 and the point P, right? R equals distance between 0 and P. And so you can directly integrate this, because you're integrated over this expression of a hole. So in polar coordinates, you integrate from 0 to epsilon. So in polar coordinate, you have to use, this is 2 pi r dr. You multiply by IA divided by epsilon minus r squared. And this you can integrate easily by indirect integration. I leave this as an exercise, and you will find that you can get exactly this quantity. In summary, what we have found, so let me remind you that W was P0 minus J0. So you can write P0 as a function of the sum of this Weber solution. This is called the inner solution. It tends to 0 inside the domain. You remember, this is like 1 minus constant divided by a rho. So this eliminates, this solution disappear far away at a certain distance. But what is interesting is that you now know exactly what are these coefficients A, because they have been calculated through this matrix. And you have what is called the outer solution, that is the solution outside, which is given by the Green's function. So now let's do quickly an application. So how do you apply this method? So you can try, let's say for 3 hole, n equals 1, 2, and 3. So for 1 hole, it's very easy. You take this Green's function, you take the Green's function at the center of the hole, you multiply by this arc sign, and you see that the flux, that is the amount of particle, if you are at a distance x0, this is x1, and you have Brownian particles that are emitted, and if you look at the fraction of them that reach the holes compared to those that are escaping to infinity, it depends on the size of the hole and the distance between 0 and 1, x0 and x1. Now, if you are with 2 holes, n equals 2, we have to sum over the 2 Weber solution. You have a matrix to invert. That's, I'm giving you already the solution. This is given by the coefficient A1 and A2. And alpha 1 and alpha 2 are the Green's function calculated. So alpha 1 is minus the Green's function calculated at position x1, x0, and alpha 2 is minus the Green's function calculated at position x2, x0. And d epsilon is this quantity. And then you can calculate the flux. And you can see, for example, for phi1 can be expressed with this expression. So this is, we can recover the first term, which is what we had for 1 hole, plus a correction due to the presence of the second hole. And now let's finish with the case with 3 holes, where you have to expand over this 3 Weber solution. Then here you have to invert a 3 by 3 matrix equation. So I let this as an exercise. You can find the coefficient A1, A2, A3, where the Dij is given by this expression, and the determinant is given by this. And so now if you write the flux, and this is an interesting expression, you have the flux, the number of particles, if you start at position x0, that will escape from hole 1, 2, and 3. The 3 of them have a size epsilon. And what can you see here? The flux, the number of particles split between 1, 2, and 3. And some can, of course, escape to infinity because you are in dimension 3. And this is the first order term with expression epsilon. This is the second order with expression epsilon squared. And suppose for 1 second we neglect this second term. So if suppose you know the flux phi1, phi2, and phi3, can you reconstruct the position of the source x0? Well, this is you have to invert this expression, which is very easy because you have x1 minus x0 equals 2 epsilon pi divided by the flux phi1, and so on. So which means that if you construct the ball center at x1 with this radius, so this is this radius r1, you obtain 1 ball. Then you do the same with x2, which leads in dimension 3, this is a circle. And then if you have 1 more, so this is 1, this is 2, and now we need, let me change color, we need 1 more, and this will give you a third surface for 3, and you have this intersection. So this shows that you can invert these equations, and from the fluxes phi1, phi2, and phi3 found the position of the source. And if you consider the other terms, this intuitive reconstruction works. And in the next presentation, I'll explain more about how this can be done, not only on the plan, but also on any surfaces. And so we call this is called the flux coordinates. So allowing that, for example, a cell that would be able to estimate the fluxes at each of their position where they can sense Brownian particle, in principle, mathematically, they can reconstruct the position of the source. So if you're interested, I invite you to have a look at the present literature that we have written over the past years, where we explain this. This is Dobramysl and myself in Journal of Computational Physics, scientific report. Last year we had this in dimension 3 in PRL, and we have here a recent review that summarizes all of this information. And if you are interested in general about match asymptotics, I refer to the very important books of Bender and Orczak, that wrote this book about advanced mathematics for engineers, where they summarize the general idea of match asymptotics. Here I wanted to show a specific example on the Laplace equation. Thank you.